minimal stress is log 0, and the stress ratio is log -1, and the mean stress is log 0. And for completely reversed stress, the maximum stress equals minus the minimal stress, and the stress ratio is -1, mean stress is 0, and stress amplitude equals the maximum stress. And for the repeated stress, the minimum stress is 0, and the stress ratio is 0.2, and mean stress is half of the maximum stress, and the stress amplitude is half of the maximum stress. Okay, this is the parameters for the stresses. And also we load the stress criteria. The working stress should less than the allowable stress, and we have the safety factor S. S should less than the allowable safety factor, and the S is sigma limit divided by sigma, and this is the strength limit, and this is the maximum working stress. For ductile material, we choose the stress limit as the yield stress, and for the bronchial material, we choose the stress limit as the tensile stress, sigma B. This is for the static stress. And for the alternating stress, vertical factor failure will occur. So we will choose a new sigma limit. And for fatigue, it has 3 zones: the initiation zone A, and the propagating zone B, and the fracture zone C. And we should calculate the stress limit for fatigue fracture. And in the SM curve, we have the equation, and in this curve, it indicates that for a stress level sigma, we can have a number of cycle to fatigue N, and we have this equation. The stress criterion is S equals sigma -1N divided by sigma A should less than the allowable safety factor. Okay, and this is the sigma A, sigma N curve, and the points on the line A, F, E represent represent the stress limit, or we call it the endurance limit. And the points in the zone A, F, E, O, in this zone, the stress is less than the endurance limit. We can express as sigma like this. Okay, and the points outside this zone, the working stress is less than the endurance limit. So in this point A, it represents as completely reversed stress, and the points on the horizontal axis represent as static stress. Okay, and the point C represents the repeated stress. Okay. This zone indicates safety. But okay, this is for the material, and the line A1, F1 represents the element in the endurance limit, because the endurance limit of element is less than material, because the material is a standard sample, and as the safety factor S is the endurance limit divided by the maximum stress. Also, okay, this maximum stress can obtained from calculation, and the endurance limit on A1, F1 is for the element, and in this zone, the element is safety. Okay. Point M represents working stress, the sigma A and sigma M, and the working stress is in the zone A1, F1, E, O, and it satisfies the strength criteria. But we had a safety factor. Yeah, safety factor S equals so there should have a margin between the working stress and the endurance limit. Okay, and the value of S is less than 1. Okay, so how to find the sigma limit for this point? Below the sigma limit on the line A1, F1, and we should load the position. we can connect the origin O and the point M and extend the line to intersect with the line A1, F1 at M1. Okay, we have the safety factor can express as this, and we can calculate the safety factor, and the safety factor should larger than the allowable safety factor, and this is for the condition R is constant. Okay, R is constant, and the stress ratio is constant. But for the point N, we connect the origin O and N and extend the line to exert with the line F1E at point N1. So the endurance limit is on line N1E, and the equation about line N1E is different from the A1 and 1. Okay. So we also have the safety factor Ca equals sigma S divided by sigma max. The angle is 45 degrees, and the endurance limit for N1E is the yield stress. So there is two conditions, the M point and the N point. If connect the origin O and the point, if it intersects with the line A1, N1, we use this equation. If it intersects with line N1E, we use this equation to calculate the safety factor. And both the two conditions is for R is constant. And we also can draw a line parallel to the vertical axis, and it intersects the line A1, F1 at point M2. Okay, and for this situation, the mean stress is constant. Okay, this is. And we have this equation and to calculate the safety factor with this equation. Okay, and for point N, and it intersects line F1E at point N2, and the endurance limit is the yield stress. So we use this equation to calculate the safety factor. Okay. And we also can draw a line, and with the angle is 45 degree. Okay, the angle is 45 degree, and it set the line A1 F1 at point M3. So we have this equation to calculate the safety factor. And for the point N, we also have this equation to calculate the SCA. And for this situation is the minimal stress is constant. So we have three conditions. For sake of the mean stress is constant, we have this equation, the stable technique stress. For static stress, we use this equation to calculate the safety factor, and for R is constant, and the mean stress is constant, and the minimal stress is constant. We use these equations, and this is the point represent point M, and this represents the point M. This is represent the point N, and we can also we have unstable stress. The unstable stress may varies with time, regularly or irregularly. Like this, the stress amplitude is variations with the time, and the sigma 1 is the maximum stress of each stress level. So for this situation, we also can calculate the safety factor. And we use the linear cumulative damage ruler. And in this ruler, we assume that any stress amplitude greater than the endurance limit contributes certain physical damage to the element. And the amount of damage depends on the number of cycles at that stress amplitude and the total number of cycles that would produce failure to a standard specimen at the same stress amplitude. And when the total accumulated damage generated by different stress levels reaches a critical value, vertical failure occurs, and this is the assurance of the ruler. Okay, for the initial unstable stresses, and sigma 1 represents the maximum stress of each stress level, and N1, N2, N3 are the number of cycles acting on the element at each stress level, sigma I, and big N, big 2, big 3 are the numbers of cycles to failure at each stress level, sigma I, and this value can occur from the SN curve. And this is the stress level sigma 1, and the N1 is the number of cycles acting on the element, and the number big N1 is the number of cycles to failure, and then big N1 it can be acquired from the SN curve. Okay, and this stress greater than the endurance limit each cycle will cause certain damage. The damage contribution of N1 cycles at stress sigma 1 is assumed to be Ny divided by big N1, and where the damage contributes to N2 cycles at sigma 2 is assumed to be N2 divided by big N2, and when the cumulative damage approaches 1, practical failure ensues. Okay, you can express as Ny divided by big N1 and plus N2 divided by big N2 and plus Nz divided by big Nz reaches 1, the practical failure ensues. Okay, or we can express it as this sigma Ni divided by big Ni is 1. Okay, and the stress is smaller than the endurance limit will not cause the damage and can be neglected in the calculation. Okay, and from the SN curve, we have sigma m to the m's times m is constant, and therefore I can express as this, and substituting this equation to this equation, we have sigma Ni times sigma I to the m's equals N0 times sigma minus 1 to the m's. And assume the practical effect of variable amplitude stress is equivalent to that of a constant amplitude stress sigma v. Universally select sigma v equals sigma 1, and sigma 1 is the maximum stress, and that operates the equivalent number of cycles big NV. We have this equation. So the equivalent number of cycles Nv is then divided as Nv is sigma Ni times J divided by sigma 1 to the mth, and corresponding to the equivalent number of cycles Nv, the enduring stress for completely reversed stress sigma minus 1 Nv is to the mth root and 0 divided by Nv and times sigma minus 1. And Ks is this, and sigma minus 1 Nv equals sigma minus 1 times Ps, and we can calculate the factor Ks, and then we can calculate the safety factor. Okay, the safety factor can be expressed as sigma minus 1 Nv divided by sigma 1, and should less than the allowable safety factor, or this sigma Sa equals sigma minus 1 divided by sigma Ca, and sigma Ca can be expressed as this. So use the two equations, we can calculate the safety factor of the unstable stresses. Okay. Have an example. A rope shaft has vertical properties of endurance limit sigma minus 1 is 300 megapascal, and the material constant M is 9, and the number of critical cycles and 0 is 10 to the 7th in size. The shaft is to be subject to a spectrum of completely reversed stresses. First, 500 megapascal for 10 to the 4th cycles, then 400 megapascal for 10 to the 5th cycles. After this loading sequence has been imposed, it is desired to change the stress to 350 megapascal. Estimate the remaining cycles for the shaft at the final stress level if the duty cycle is to be repeated 4 times during the life of the shaft. So we should calculate when load the sigma 1 is 500, and sigma Ca can calculate this. So Ks is 0.564, okay, and Ca is sigma minus 1 divided by Ks times sigma 1, and sigma minus 1, okay, this is 300, and divided by 0.54 times sigma 1. and sigma 1 is 500. Okay, we can use this equation. We also can use this equation. Okay, with this equation, we also can calculate. We can also calculate this, and we also can calculate the safety factor is 1.14. We use both of the equations. And after this loading sequence has been imposed, the stress will be changed to 350 megapascal, and we load sigma 3 is 350 megapascal. So calculate the number of cycles before it breaks. So we should calculate the N3, okay, and we also have N1 times N1, N2 divided by N2, and N3 divided by N3 is 1, okay. So we calculate the big N1 and the big N2 and big N3, okay? And we load this, and we can calculate N3. So N3 is 0.97 times 10 to the 6. Okay. So we have practice. And an element is to be subject to a spectrum of completely reversed stress. First, 500 megapascal for 2 times 10 to the 6. Then 450 megapascal for 10 to the 6. And 400 megapascal for 3 times 10 to the 6. After this loading sequence has been imposed, the specimen is damaged. And if the element is to be subject to a stable completely reversed stress, sigma is 500 megapascal. Estimate the number of cycles of vertical N. Okay. We load this is for a spectrum of completely reversed stress, and this is for a. We should calculate the failure, the number of cycles to failure M for stable completely reversed stress. Okay, in the stress on the curve. Or on the Sn curve, we should calculate the N, and its stress level is sigma is 500 megapascal. We should calculate this N, okay, and we load the sigma and M for a spectral or completely reversed stress. Okay. how to calculate the number of cycles to fatigue for a stable, completely reversed stress. Can we have a rest? Rest for 10 minutes. Okay. Under a stable, completely reversed stress. And so we know from the SM curve, the M times sec for a stable, completely reversed stress. Yeah, we have this equation. Okay, and for the ruler, we have this. Okay. We have this equation. Okay, and mi sigma I is for the spectral of completely reversed stress, and m and this n0 sigma minus 1 is for a stable, completely reversed stress. Okay, and from this equation we can calculate the n0. N0 is the number of cycles to fatigue under the stress minus 1 equals to 500 megapascal. Okay, and Ni sigma I is on this. Okay, so calculate the value of N0. Okay. Use this equation we have. Okay. N0 times sigma minus 1 in the practice is 500, m is 9, okay, equals to sigma Ni 9, and equals to sigma 1 is 500, and N1 is 2 times and plus times 4 sigma 3, 400 megapascal is lower than the sigma minus 1. So it can be neglected, and we also can plus. Okay, and this is n times we can express as and we know the sigma minus 1 is 300 megapascal, and m is 9, and n0 is 5 times 10 to the 6. So calculate the safety factor. Okay, we can also use we use the safety factor calculation equation. This or this. Okay, we can calculate the sigma CA first. Okay, the sigma CA equals Ni sigma I m and then divided by n rho and zero. Okay, and SCA is sigma minus 1 divided by sigma CA. Okay, so we can calculate this value. So we know that m is 9. Okay. And n1 is 10 to the 4th. Sigma 1 is 500 and plus n2 is 10 to the 5 times 2 is 400 and n3 is 10 to the 4th times sigma 3 is 200. Okay, and then divided by n0, and n0 is 5 times 10 to the 6. Okay, and calculate. We can also have and 100 times 100 and okay, we can have this. Okay, this express like this. Okay, and then we can divide it by 10 to the 6, and this can and this can be 0.1 and So calculate this. How many? Calculate this. Okay, so the sigma A is okay, and then we calculate the safety factor. Okay, and the safety factor SCA equals sigma minus 1 divided by sigma CA, and sigma minus 1 is 300, and sigma CA is, and calculate the safety factor is 1.089. Okay, so we calculate the safety factor. Okay. And this is use this equation, and we also can use the equation equals sigma minus 1 and v divided by sigma minus 1. Okay, we also can use this equation, and we can calculate the equation. And we also can calculate, use this equation, and the answer is also 1.089. Okay, so we for a spectrum of complete reverse stress, the safety factor use this equation to calculate. Okay, this is the answer. So below the safety factor calculation equation for static stress, and for R is constant, sigma m is constant, and maximum stress is constant, and we also can have the unstable stress, the safety factor can express like this or this. We can use these equations to calculate the safety factor for unstable stress. Oh.
Yeah.
This?
Yeah.
And -1. -1. This sigma -1 and weight divided by sigma 1. Now these two equations can calculate this. And for this practice, we also can use this equation. Okay, it's the same. Below the sigma -1 and weight in this equation. Sigma -1 and weight can express as sigma -1 times m and 0 sigma 1 to the m's power. Okay, and then divided by sigma 1. Okay, the SCA use this equation can express like this. Okay, sigma -1 LV equals sigma -1 times this. So SCA equals this time divided by sigma 1. And this sigma 1 and this sigma 1 can this. Okay. And equals sigma -1 and 0 divided by ni sigma I m. Okay, and for this practice, the sigma -1 is 300. Okay, and times m is 9, and n0 is 5 times 10 to the 6, and divided by n1 is times sigma 1 is plus n2 is 10 to the 5th times 400 to the 9th, and sigma 3 is too small. Okay, and we can calculate this. Calculate is equals 3 times 9 Okay. This can change into this. Okay. 300 and this can 100 divided. And we also can this and this can change it into, and this can change it into. Okay. Okay, and it equals to 3 times 9, 5 divided by, this is plus right, this equals this and this, and we can also have this. This is equals 3 times it's also 1.089. Okay. So okay, we use this equation to calculate the safety factor. The value is also 1.089. So both this equation and this equation can calculate the safety factor. Okay, it's the same. Okay. Now we know some situation to calculate the sector factor, and this is for the static stress. Okay, for static stress, the sigma limit for brighter, this is sigma B. For ductile, this is sigma S. Okay, so for ductile material, the sigma limit is the yield stress, and for brighter material, the sigma limit is the tensile stress, sigma B. Okay, and this is the safety factor calculation equation for R is constant, and this is the this condition is for the point M. The sigma limit is on the line F1E. Okay, it's on the line F1E. We have the sigma A, sigma M curve. Okay, and this is point A, and this is F4 element. This is A1, and this is F1, and this is point E, and point E represent the static stress station, and the stress is sigma S, and for A represent the completely reversed stress, and the value is sigma -1. Okay, and For the point M, represent the working stress state. If the stress limit or endurance limit is on the line A1, F1 in this line, and for R is constant, we use this equation to calculate the SCA. And if for point N, the endurance limit is on line F1E. On this line, the angle is 45 degrees. Okay, and on this line, the endurance limit is sigma s. Okay, equals to this. Okay, and we use the right one to calculate the SCA. Okay, and for sigma m is constant. We also, if the endurance limit is on line A1, F1, we use this equation. And if the endurance limit is on line F1E, we use this equation. Okay, and for sigma minimum is constant if the endurance limit is on line A1, F1, we use this equation. And the endurance limit on line F1E, we use the right equation to calculate the safety factor. Okay, and this is for the stable stress, stable cyclic stress. Okay, but for unstable cyclic stress, we use the two equations to calculate the SCA. Okay, and the result is the same. Okay, and then, but for most meshing element, but for this label, for this, okay, and this is for the okay, this is the strength criterion for static strength. Okay, but this is for combined stress. This equations is for uniaxial stress. The element is subject to tension or to tearing. And for combined stresses, the stress criteria can use the fourth strength theory can express like this, or use the third strength theory like this. And this is the equation for combined stress with constant amplitude. And this is the endurance limit diagram for combined stress. And the safety factor S can be expressed as this. And before calculate the safety factor, we first calculate the S sigma and S tau, and calculate this value and this value, and then calculate the safety factor for combined stresses. Okay, so this is the for combined stress. we use these equations to calculate the safety factor. And this is for static stress, and this is for fluctuation stress. Okay. So this is the so if we want to calculate the safety factor, we should know the stress state. Okay. And then measures to improve vertical stress, we know the vertical influence factor K sigma. K sigma equals this, and the little k sigma indicates the vertical stress concentration factor, and epsilon sigma is size factor. Beta sigma is surface condition factor, and beta q is intensifying factor. Okay, this is consideration the stress concentration, usually induced by geometrical discontinuous like keyword, holes, or shadows on an element. Okay, if the value of this factor increase, and the vertical influence factor big K sigma increase, and the vertical stress of the element will decrease. Okay, and the size factor epsilon sigma is considered the element size. If the element size increase, and this will decrease, and the vertical influence factor will increase, and the vertical strength of element will decrease. Okay, and this is the surface condition factor. If this increase, if the surface condition is good, so the value is large, and this factor will decrease, and the vertical stress will increase. And this is intensify factor, and this is considered the surface treatment. Okay, and like surface called rolling. Okay, if any surface treatment will increase this factor, so decrease the particle increase factor, and can increase the vertical strength of the element. So the actual endurance limit of a meshing element will then be sigma minus 1e, indicate the actual endurance limit of a meshing element equals sigma minus 1 divided by the vertical influence factor. Okay, so the methods to improve vertical strength, it can reduce stress concentration and select a material with high endurance limit, and improve manufacturing quality to reduce initial micro cracks, and can increase surface strength by surface treatment. So this is the methods to improve vertical strength. Okay. Okay, let's have practice. Completely the statement with the correct phrase. Which one of material is chosen for evaluating the vertical stress of melting element? A. The yield stress. B. Endurance limit. C. Ultimate stress. D. Elastic limit. Which one? For vertical stress, choose which one? Endurance limit. Okay. Endurance limit is chosen to evaluate the vertical stress. And the yield stress is for ductile material under static stress. Okay. And the ultimate stress is for grinded material under static stress. Okay. And this point M represents the working stress of an element. If the minimal stress is constant, the endurance limit locates on point M1, M2, M3, or M4. Under the condition sigma, the minimum is constant. Which one? In our sigma A, sigma M diameter, okay, in this sigma A, sigma M curve, okay. This is the point M represent the working stress, okay. So, how to find the sigma limit of point M? Say if sigma, the minimal stress is constant, we have considered three conditions. Okay, if R is constant and sigma M is constant and sigma minimal is constant respectively. Okay, and for the condition the minimal stress is constant, how to find the sigma limit? How to find the sigma limit? If we know if R is constant, we connect the origin O and the point M, okay, and insert with the limit line, okay. This is for R is constant. And for sigma M is constant, we draw a line perpendicular to this line, okay? And this point indicates the sigma limit for this, okay, for this condition. And when the minimal stress is constant, we draw a line with a angle is 35 degrees. Okay, so which point represent the endurance limit? This line is M2. Okay, it's M2. If this is, if R is constant, we choose which one? R is constant, we choose connect O and M, okay, and M3, okay. If sigma M is constant, we choose the perpendicular line M1, okay, okay. So M1 is for the condition sigma M is constant, and M2 is for the condition the minimal sigma is constant, and M3 is for the condition R is constant. Okay? Okay. Okay, so have a rest for 10 minutes. Okay. It's the three situations for fluctuating stress and how to find the endurance limit or vertical stress. And let's summarize again. And for static stress, we the maximum stress should less than the allowable stress. And for fluctuating stress, we should ensure a sufficient margin between the working stress and the stress limit. Okay. For example, this is the working stress, and this point M1, M2, and M3 is the vertical stress or endurance limit respectively, and there is should sufficient margin, and this margin is safety factor. Okay, is safety factor S, and the S usually is 1.2524, and it's the factor value. And so, if an element with a working stress located in the zone A, FE, FE1, EO represent the working stress is less than the stress limit. Okay, but we should consider the S. If the sigma, if the limit, the stress limit divided by the maximum stress, if satisfy the allowable safety factor, and the safety factor, we can calculate the safety factor under the working stress and then compare it with the allowable value. Okay, and this is the condition for static stress and fluctuating stress and unstable fluctuating stress, and this and this is for uniaxial stress. Okay, the element is subject to a tension or to a shear stress. But for the combined stress, if the element is subject to a tension and a shear stress, we use these equations, and the two equations is for the static stress, and this is the fluctuation stress, and this means the tensile stress and the shear stress is static, and this means the tensile stress and the shear stress is fluctuating stress. Okay, and use this to calculate. And for static stress and for a ductile material, the value of S is 1.5 per 2.5. This is for material. But for element, the value is 1.2 to 1.5, and this is for an element. And for brighter material, and under static stress, the value is 3 to 4. And for fluctuating stress, the value is 1.3 to 1.7, and this is a lower value. Okay. And the SM curve is to calculate the number of factor to failure. Okay, under the stress level sigma I, we can find the number of cycle to failure on the curve. Okay, and the stress criteria can express like this. And for spectral stress, we can express like this and use this or this equation to calculate the number Ni or number big N V. Okay, and these are consider the element vertical and uniformly for body factor or body failure. Okay, but some element has the surface failure. Okay, and this we should consider the contact strength. Okay. For example, the messengers and the rolling contact variance uniformly fatigue on the uniformly failure on the surface. Okay, we should consider the contact strength. And this is the heating on the surface. And when curved elements are loaded, contact error deviate elastically from the basic surface curvatures, and high contact stresses are correspondingly developed with small contact error, and we also can calculate the contact stress. Use this equation. This equation to calculate the contact stress, and mu, E, and rho are Hess's ratio, elastic modulus, and the radius of curvature respectively, and subscript 1 and 2 refers to the two cylinders, and the negative symbol refers to an interior surface, and the positive symbol refers to an exterior surface. Okay, and so it's this calculation for contact stress, and this is used application for gears or shafts. Okay, this is all about the strength of element. Okay, unit 2. And in unit 3, we will study the screw joints and the screw. Okay, and we will watch a video. Okay, but there is no sound. Okay, I need help.
Start. Where you bend the wire upward and downward repetitively.
Start.
Your answer
okay.
is obviously the second op. Consider this mechanical parts. Even if you design them while satisfying mechanical strength criteria, it may fail due to a phenomenon called fatigue. Historically, many design disasters have happened by neglecting effect of fatigue factor. To understand what is fatigue, let's consider this metal wire. You have to break it. So how will you break it? Will you pull it from both ends, or will you do this? Where you bend the wire upward and downward repetitively. Your answer is obviously the second option, because this method requires less effort compared to the first case. This is a well-known example of fatigue failure. So how does material fail due to fatigue? To get answer for this question, let us have a close look at stress variation in wire cross-section. When you bend it downwards, bending stress is induced in the wire. It will be tension at top area and compression at bottom area. When wire is at equilibrium, there will not be any stress on wire cross-section. When wire is bending upwards, there will be compression at top and tension at bottom. So if you trace stress induced at a point with respect to time, it will vary like this, as a fluctuating stress with time. Initially the point will have positive stress. After that zero, then negative stress. The same cycle repeats again and again. Such fluctuating stress is the root cause of fatigue failure. When such fluctuating stress acts on a material, it will initiate something called micro crack. This crack will begin to grow with fluctuating load, and over time it will cause an abrupt failure. This is why failure due to fatigue is a dangerous affair. Unlike failure due to static load, fatigue failure happens without any warning. It doesn't even make a neck, and the failure is completely unpredictable. The same phenomenon can happen for axle of this motor, where it is undergoing fluctuating stress due to gravity effect of this mass. This rail wheel, when it is contact with the track, produces a high contact stress. But when the wheel rotates, stress gets relieved. When it comes back to original position, contact stress arises again. So this also is a case of fluctuating stress. It may fail due to fatigue if we do not design it properly. Same is the case with gear pair. Here contact stress arises at mating point. Now, the most important part in fatigue analysis, relationship between stress amplitude and number of cycles it can execute before it fails. What will happen as stress amplitude decreases? Yes, you are right. As stress amplitude decreases, number of cycles required for failure increases. Anyway, we will analyze this trend more systematically. We will draw number of cycles in x-axis, stress amplitude in y-axis, both in logarithmic scale. Let's start with the maximum stress a material can withstand, its ultimate stress. So this will happen as you increase the stress. Even before completing one cycle, the material will get broken. So this will be the corresponding point in Sn graph. If you decrease the stress amplitude, it will execute more number of cycles before it fails. Decreasing stress even further, it will be able to execute even more number of cycles. So this will follow a trend like this. But not forever. You can see after a particular stress amplitude, even with slight decrease in stress, number of cycles required to make it fail increases drastically. Or in short, if you have stress amplitude below this limit, number of cycles to make it fail jumps to infinity, or material never fails after this limit. This limit is known as endurance limit. Below endurance limit, it is safe to operate the material. Engineers always try to design the components by keeping stress amplitude below endurance limit. You can see that endurance limit is way below ultimate stress value. It is a good approximation to consider these two regions as linear. But here we have a case of complete stress reversal, where stress mean value was 0. What will be the maximum stress limit for this case, where stress reversal does not happen? It has got a mean value and amplitude. For this purpose, we have to use something called the Goodman diagram. In the Goodman diagram, mean value of stress is drawn on x-axis. Amplitude of stress is drawn on y-axis. When mean value is 0, we know safe stress limit is same as endurance limit. When amplitude of stress is 0, it is same as a static loading condition. So safe limit for tension is ultimate tensile stress at tension, and safe limit for compression is ultimate tensile stress for compression. According to Goodman analysis, safe stress amplitude limits for all other cases lie on straight lines connecting these points. So for a particular stress mean value, we can find what's the maximum allowable safe stress limit from this diagram. It will be here. Similar analysis can be done considering safe limit of amplitude 0 condition as yield strength of material. This is known as Soderberg diagram. Generally, Goodman analysis is the most preferred one. To learn more on fatigue failure, check the second video. Thank you.
Components are exposed to periodically varying loads without us being aware of it. The crank arms are alternately under load, then swing back almost load-free, are under load again with the rhythm of pedaling. The spokes, the pedals, even the individual links in the chain are stressed periodically. Also, the railway bridge over the River Rhine, seemingly totally addressed, alternately has to bear the additional burden of a heavy freight train and then only its own mass. Aircraft experience quite different stresses during take-off and in turbulence than on the ground. This type of loading is generally termed fatigue loading, and the material responds to it, fatigue. The term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is. Each day, thousands of items break due to cyclic, often repeated loading. How can we make sure that all these components withstand the cyclic loads? To achieve this, one has to test the materials appropriately. We intend to measure the fatigue strength of a frequently used steel in our laboratory. Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters. The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks up the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with 2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted, and there in turn a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals 2 regions, the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks, starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. Of course, now we want to know how many load cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. He chooses a higher alternating load for the second specimen, a tensile force of 7.5 kilonewtons and a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to failure. The third specimen is only tested with a cyclic load of 6.5 kilonewtons. Under this reduced load, it does not break even after 3 million load cycles. Additional specimens complete the series of measurements. Some of the specimens are tested with the same load we've already used. In this way, we get an impression of the range of scattering. To compare materials in a fair way, the different cyclic loads are converted to the respective stresses acting in the specimen. In this case, the stress alternates sinusoidally around the mean value, which is termed mean stress sigma m. In this series of tests, the mean stress is 0. The stress amplitude is labeled with the symbol sigma a. For graphical representation, the SN diagram is used, also termed Wöhler diagram. In an unusual manner, the predetermined variable is plotted upwards on the y-axis. It is the stress amplitude sigma a. And the result of the test, the number of cycles to failure n, is plotted to the right on the x-axis. To fit small and large numbers into the diagram, the x-axis is not scaled linearly, but logarithmically. The first specimen was loaded with 7 kilonewtons. This corresponds to a stress amplitude of 248 newtons per square millimeter. Under this stress amplitude, it broke after 381,000 load cycles. The second specimen was loaded with 7.5 kilonewtons. This corresponds to a stress amplitude of 265 newtons per square millimeter. Under this stress amplitude, it broke after 43,600 load cycles. And these are the results of the other specimens which have been tested by us. When additional specimens are tested and the results are displayed as a curve, it becomes clear that this material will not break below a certain level of stress amplitude, even after a very large number of cycles. This stress level is termed fatigue limit sigma capital A. For most steels with body-centered cubic structure, the fatigue limit is reached after 10 million load cycles at the latest. It must be noted that the experimental results scatter considerably. Therefore, instead of a sharp curve, a statistically defined scatter band is commonly used. Of course, most users don't load their components with a constant cyclic load, but rather in an irregular manner. Therefore, these components have to be tested under this type of loading, termed operational loading. In this test rig, critical bicycle components are loaded similarly to practical use. Stem and handlebar must endure the typical bending and torsional loads for a sufficient number of cycles. Only then they are approved for serial production. Moreover, the fatigue strength does not only depend on the material. The mean stress has an important influence, the shape, the surface quality, environmental conditions, and much more. Not an easy story. Before an aircraft is allowed to take off for the first time, it has to go through extensive stress tests. The wings and many other elements are cyclically loaded in large test rigs. This later ensures the safe operation of the aircraft. Nevertheless, particularly important components are repeatedly examined for fatigue cracks in the course of operation. The tram, for instance, has to go to the test hole at regular intervals. Experienced staff use ultrasound to examine special components, especially the wheel set axles, to check whether they are still in perfect condition. Aircraft are also inspected for fatigue cracks at reasonable intervals. This helps us to depart for air travel without worry and land again safely.
types of screw thread and standard joint, tightening of screw joints and loosenings, preventing of screw joint, strength analysis and design of joint, and materials and measures of improve intensity of screw bolt joint and screw drive. First, the forming of screw thread. Okay, for chemical line, the loopers of a moving point which rotates around the axis and at the same time moves along the axis in constant velocity on the surface of the cylinder, and the screw thread is a play finger, moves along a helical line and cables itself through the axis of the cylinder when moving, and the screw thread is forming. Okay. This is the screw thread. Okay. And the types of screw thread, there are many classification. According to the types of tools of screw thread and the direction of rotation or the direction of helical line and the number of helical line and the position of the screw thread and the function and the shape of body of revolution. So, according to the type of tools of screw thread, it can divide into a square screw thread, triangle screw thread, terpene screw thread, and buttress screw thread. Well, this is the square thread, like this, and this is the triangle thread, and this is the terpene thread, and this is the buttress thread. Okay. And for the direction of rotating, we can divide the thread as right hand thread and left hand thread. And for the left hand thread, the direction of helical line is clockwise, and this is anti-clockwise. And this is according to the number of cut line, and this is a single start thread, and this is a multi-start thread, and according to the position of thread, we have external thread and internal thread. And this is internal thread, and this is external thread. And the internal thread is the thread on alert or threaded whole, like this. And the external thread is the thread on a screw, like this. Okay. And for the function, according to the function of thread, there is a joint screw thread and driving screw thread. And this thread is used for for joint the members, and this is for driving the force or torque. But this is a joint screw thread, and this is a driving screw thread. Okay, and the triangle thread is a joint screw thread, and the square thread and the titanium thread and battery thread are both the driving screw thread. And for the square thread, it has the greatest strength and efficiency, but it is difficult to fabricate. And for the two threads, they are easier to manufacture, and for the tryptophan thread, it is selected to carry bidirectional loads, and this purchase is selected for the unidirectional loading. Okay. And for the sake, according to the sake of body of revolution, I have parallel screw thread and taper screw thread. This the parallel screw thread, and this is the taper screw thread. Okay. The primary geometric parameters of screw thread. One is the major diameter D, and the major diameter D is the largest diameter of the screw thread D, and the minor diameter D1. Minor diameter D1 is the minimum, the smallest diameter of the screw thread, and pitch diameter D2, and for the pitch diameter D2, the width of the thread and the groove are equal. And the thread pitch T is the actual distance between corresponding points on adjacent threads, and lead S. And lead S is the actual distance the thread will advance in one revolution. And for multi-screw thread, S is M times T. Okay, and the lead angle force is the angle force is the angle force is the angle force. This is the angle force. The angle force is the angle between the perpendicular of the axle and the rise of the thread, and this is the angle, and tank force equals MP divided by pi d2, and d2 is the pitch diameter, and included angle alpha, and included angle alpha is the angle between the flanks of the adjacent thread, and the flank angle beta is half of the angle alpha. This is alpha and this is beta. And contact height h. Contact height h is the radial distance between the major diameter and the minor diameter. There is h. There are 3 grades for screw thread: A grade, B grade, and C grade. And for A grade, using for small tolerance, highest pressing using in the occasion that the feed is pressed. And for B grade, and for very heavy load and be disassembled or adjusted frequently or very variable load. And C grade is in most common use. And we also can divide the screw thread into coarse thread and fine thread. This is fine thread. Okay. And the coarse thread is applied most widely. The advance of fine thread is the lead angle is small and the minor diameter is great, and the capability of self-locking is good, and the degree of strength is high. And fine thread have a better capability of resisting losing from lubrications because of the smaller lead angle. So they have a smaller depth and large root diameter that provide higher static tensile stress. This is blank angle bed. And for the twisting screw thread, the beta is 50 degree, and for the battery screw thread, and the beta is 3 degree. Okay. This table indicate the characteristic about the 4 types screw thread. And this is the flank angle bed. For triangle is 30 degree, and for square is 0 degree. And this the self-locking. Self-locking for triangle thread is very good. 1 is represent best, 4 is represent the worst. And so for the square thread, the self-locking is the worst. But for the square thread, it has the best efficiency and versatility, and its root strength is the worst, and the root strength of triangle thread is the best. Okay. Both the joints apply when one of the jointed components is too thin to drill a body-sized hole. And the screw joints cannot be disassembled frequently, and the stud joint can be disassembled frequently by removing the nut and the washer. without damaging the threaded member. And this is the parameters of the bolt. Screw depth in base edge when screw is burstier or furlong H equals D, and for cast iron H is 1.25 to 1.5 D. And for aluminum alloy, H is 1.5 to 2.5 D. And the depth of screw hole H1 is pressed as this. And is the depth of draining H2 pressed as this. Okay. And the holding screw joint or set screw joint, like this, is designed to be inserted into a tapped hole to bearing directly on the making element. And the screw depends on compressing to developing plating first to lock components into place. And they should not be used in vibrating applications where losing would impose a safety hazard. Okay. And this is the screw thread fastener, and this is a bolt. This is a hexagon paired bolt, and this is the structure of bolt. Structure of bolt. There are many types, and stud. This is A type, and this is B type. And L1 is the length of 1/8 fating in the base, and L0 is the length of a large end fating in the large. This is for the screw. And the screw. These many types of the screw. This is the hand, and this is the end of the screw. And this is the special screw thread joint, the foundation bolt, or T-type bolt, and nut. Yes. Types of nut. This is a round nut. Okay. And this is other nuts. Other nuts like this or this. Also are the nuts and the washers. The function of washers is to increase the bearing area in order to decrease pressure. This is a plain washer, and this is thin plain washer. And A type, and this is B type. And this is spring washers. Yes. Yes. Okay, this is the types of screw thread fasteners. Okay. Okay. Today class is over. Okay.
You shared this PPT in your group.
I shared the PPT. You can